Well, we are gathered here for Utkarshani's dissertation defense. I'm particularly delighted that one more of the committee members is here in person. Corey Hansen is here in person from Bosch. Usually, I had imagined he would be online, but it was a surprise today to see him sitting here. And with that, I know Valerie is online, Michael is online. The committee is here, and we all gathered here. So, Utkarshani, take it over.
Just to clarify, are you okay with quick questions during the presentation?
Yes. Yeah.
And bigger questions at the
towards the later part of the presentation?
Very good. Thank you.
Thank you, everyone, for joining today, person and people joining online for my dissertation defense on causal neurosymbolic AI, the synergy between neurosymbolic and causal AI, excuse me. My committee comprises of my advisor, Dr. Amit Sheth, who's the NCR chair and professor at Computer Science and Engineering, and who's also the founding director of the AI Institute here at the university. My committee chair is Dr. Marco Voltorta, who's a professor at Computer Science and Engineering Department here at the university. My other committee members comprise of Dr. Michael Hunes, who's joining us online. He's the NCR Distinguished Professor Emeritus at Computer Science and Engineering, and Dr. Valerie Shallon, who recently received this prestigious award of Brett Golding Distinguished Professor of Research, and she's a professor at Department of Psychology at Wright State University. And my industry collaborator, Dr. Corey Hansen, who's the lead research scientist at Bosch Center of AI, and he's able to join us in person here as well. So this is my thesis statement. A causal neurosymbolic AI approach fuses neurosymbolic AI with causal AI to provide an effective mechanism to transform causal concepts and information to neurosymbolic AI representation to enable advanced expression and explainability, leverage neurosymbolic AI representations and methods to solve causal AI tasks, and evaluate these methods and ensure satisfaction of causal assumptions and constraints. Before I go deep into my presentation, I have a quick question to ask everybody in the audience, and people online, feel free to join. What if I give you a choice between chocolate and peanut butter? Which one would you choose? Personally, it's a tough choice for me. I like both of these. I like chocolate, I like peanut butter. So if you want to ask me to choose between two, it's a difficult choice. On the other hand, what if I tell you you can get chocolate peanut butter cup, best of both worlds? You don't have to choose, right? And that's what exactly I call causal neurosymbolic AI. It is the best of both worlds, the two worlds being causality and neurosymbolic AI. This is just the trailer. I'm going to go deep into this concept in the future slides. This is going to be the outline of my presentation. So I'll give you a glimpse of my research journey so far. Why do we need causal neurosymbolic AI? What motivated me to look into causal neurosymbolic AI? Before going into detail, I'll give you a primer on some of the concepts that we'll be using throughout this presentation. Then we'll dig deep into causal neurosymbolic AI, its representation, expression, inference, and how do we evaluate these methods. Then I'm going to talk about some of the scholarly contributions I have made throughout this journey, and then we'll end up with acknowledgement. So I started my journey working on a healthcare project with Dayton Children's Hospital on K-Health for personalized knowledge-enabled personalized healthcare. And I was fortunate enough to Dr. Sheth and grateful to Dr. Sheth for giving me an opportunity to coordinate his NIH R01. I was just out of undergrad, and this was my major project. So this was a huge responsibility for me to deal with, and for him to give me that possibility. So in this project, we worked with pediatric sleep and pulmonology expert and some nurse practitioners to recruit 150 pediatric asthma patients. And we were interested in, we wanted to motivate or in a way make the kids capable of self-monitoring their asthma and manage their asthma in a better way. We had a kit which we called as a K-Health kit, which consists of some off-the-shelf sensors. We developed an Android application which would ask them questions about what are their symptoms level, how good they are doing during the day. So the app was personalized to ask them questions about their medication use and so on. Asthma is typically triggered by, or most likely triggered by, the outdoor allergens. So we also collected their outdoor environmental parameters such as pollen, using their zip code they were living in, their ozone, their air quality index. And I could develop a personalized Bayesian inference model. So given the past data that I have collected, how likely the patient is to get an asthma exacerbation, similar outdoor condition will arise in the future. Still correlation based, if something is would have a, in the past, if the patient had a high or had an exacerbation when the pollen level was high for through most of the time, it's highly correlated that the next time, and highly likely that the next time the pollen was high, they would still have an asthma exacerbation. But I wanted to look into causality. What is causing this asthma exacerbation? Is it truly the pollen, or what about the other outdoor allergens which are present there, such as ozone, air quality index? So this project motivated me to look into causality. I got an opportunity to work with Bosch on an internship with Dr. Henson here. And I was coming from the Bayesian modeling perspective, and he was coming in from neurosymbolic AI perspective. So I thought to myself, and the domain that we would work on was autonomous driving. So I thought to myself, are there any causal associations or relationships which exist in autonomous driving? And how can I contribute into this neurosymbolic AI framework? And that's where I came up with a causal graph, causal knowledge graph, which captures the causal concepts and relationship from the domain of causality, which is the Bayesian network, into the neurosymbolic AI space. So satisfying both my need of doing causality and his need of incorporating neurosymbolic AI in the project. So I developed a causal knowledge graph for this autonomous driving scenario, which would also capture some of the counterfactual situations which can happen. Having worked with, or having gotten some experience working in neurosymbolic AI, I wanted to dig deeper, or in a way, look into some other use case areas. So I got an opportunity to work on the industrial metaverse project at Siemens in my next summer internship. And I was again fortunate enough to be part of the very first team at Siemens who was looking into industrial metaverse. So the problem they were dealing with, they wanted to develop this metaverse framework or this metaverse setup where they wanted to see the aerodynamics of a car in the wind tunnel. And they have a lot of moving components in that project. They had the CFD simulation, which was the computational fluid dynamics of how does the car speed or the velocity changes with the wind speed and velocity in the wind tunnel. They had the graphical part of it, that was the USTs, which is universal scene or description language. So if you have seen Pixar movies, the graphics designed for those Pixar movies are based on the USD files by NVIDIA. And I developed industrial metaverse knowledge graph for them to capture all of these moving parts to eventually help them promote interoperability in the future. I continued my collaboration with Bosch in the next internship I did. That's where I laid the foundation of causal neurosymbolic AI, where we looked into this collision data set. So this is a benchmark data set. And we used causal neurosymbolic AI for explainability in those collision scenes. So if the collision has happened, what caused this collision, and what would be the subsequent effect of the collision that has happened in the scene? I had been very grateful and fortunate for all these real world applications that I was able to work on. The next one and the last one being the smart manufacturing, which was in collaboration with the next team here at McNair Aerospace Center, where we looked into causality as in terms of root cause analysis. So at the McNair Center, they have this smart manufacturing setup. There are 4 robots which are assembling a toy rocket. And an anomaly can occur in this assembly pipeline, which is any of the toy rocket part missing. And I wanted to look into this particular framework and figure out, can I do root cause analysis? Can I develop a causal knowledge graph, which would tell me if an anomaly has occurred, what caused it, which robot caused it, what was the sensor value associated with it? However, in this dissertation and today's presentation, I'm going to mainly focus my work on this clever or this collision data set. I deeply resonate with Dr. Yuda Pearl's quote that to build intelligent machines, we need to teach them cause and effect. There's a lot of work these days, a lot of hype that we've already achieved AGI, we have already achieved ASI, but to truly build those systems to be, or truly we have achieved artificial intelligence, they need to have this understanding of cause and effect, which again resonates by also being reiterated by Dr. Gary Marcus, where he said, AI needs fundamental representation of space, time, and causality. And in short term, what it will help us do would be analyze or explain the results of the machine learning model. And in the long term, it will actually help us achieve AGI, that is artificial general intelligence. There's been a lot of work done so far in the space of, in the realm of space and time, but causality is still an open research problem. Let's look into causality in real world application, taking driving application as an example. So this is a typical scene that we all encounter in our day-to-day life whenever we are driving. We do see a stop line marking, where there is in this particular scene, there's a couple of pedestrians who are walking, a pedestrian is standing, there's a car which is stopped. Do you identify, or do you think there are any causal relations in this driving scene? There are, but when we are in that particular scenario at the stop line marking, we are not thinking about causality. We never thought that some causal relations exist in those scenarios or these scenes. So there are three causal relations which can exist between the entities or events. So the presence of the stop line marking, which is an event in this case, causes the event of the pedestrian crossing the street. And both the presence of the stop line marking and the pedestrian crossing causes the car to stop. So there are three causal relations among these three different entities. Now let's take another example. So there's a car driving and the car sees a huge speed bump on the road. Car keeps on driving. Car sees trash on the road, keeps on driving. However, car sees a ball on the road and the car stops. Why? The only causal relations that we know which causes the car to stop is the presence of stop line marking and the pedestrian crossing the street. We do not have any information about any object or a ball causing the car to stop. So why? Let's look into some of the domain knowledge that would come up with this particular scene. So if we transform this scene into and create a driving scene knowledge graph, which has been in-house by one of my colleagues here, we get this additional information about the scene. We know the location where the car is driving, and that location is a residential neighborhood. People live in the residential neighborhood. Children are a type of people, and children play with ball. That's it. We still don't have any causal association or relation between these. We can combine or embed this driving scene knowledge graph with the causal relations that we have identified in the causal network that we just saw. So now we have this additional relation of the scene includes the stop line marking. Stop line marking causes the car to stop. Stop line marking causes the pedestrian to cross, and both the stop line marking and the pedestrian causes the car to stop. And from here, we can further traverse our path into the knowledge graph and deduce the fact that children are a type of pedestrians. They participate in the pedestrian event, so that are more likely they might jump in and cross the street. So there might be kids in the vicinity. That's why the car stopped, because there was a ball in the scene. So we learn causal relations among unobserved entities in the driving scene with the help of the existing causal Bayesian network that we had seen and the additional domain knowledge. What we just did is a type of causal discovery problem. where we learn the structure of the causal network, or given the structure of the causal network, you are trying to learn new causal relations. So typically, given the observation data, we have the traditional causal structure learning algorithm, and we learn a causal network based on that. But practically speaking, it's impossible to observe everything around in the world. So observation data might lack some of the parameters which should be captured. And due to that, the network that we are going to learn would have some incomplete edges or incomplete nodes. To supplement that or to account for that, what we can do, we can provide domain knowledge as a prior. So we can ask the domain expert, if you know any causal relations which needs to exist in the network, can you please provide that? And they can start with, give us, yes, even if the algorithm does not give you an edge between two nodes, there has to be an edge, and you assign, you purposefully set that edge to be true. However, access to the domain expert is expensive in terms of cost and time. So let's think about the healthcare example. It's just impossible and unreasonable for us to give the clinician the bunch of data that we have created or have collected and ask them, can you identify the causal relations and give it to them? They're already overloaded and overstressed, and overburdening them with the data analysis, it's not a feasible solution. So knowledge graph comes here for our rescue. It's a graphical representation of real-world entities and relationship between them. It contains domain knowledge. It can supplement for the missing observations and unavailability of the domain expert. And we can use knowledge graph completion problems or the setup to learn a complete causal network. We transform the problem of causal discovery from the causal AI space into the problem of causal link prediction that exists in the knowledge graph space. So here's a quick snapshot of what the framework would look like. We start with an incomplete causal network. We transform that causal network into a causal knowledge graph along with the domain knowledge using the causal ontology that we have developed. We use the knowledge graph link prediction techniques. So we have several different types of them. We have weighted and unweighted. I'm going to talk about it in the future slides, and we can use those to complete a causal network. So before I move forward, I'm going to quickly talk about some of the concepts that I will be using throughout this presentation in regards to the domain of causality. So I'll first start with a causal network. So a causal network is a causal Bayesian network where the nodes represent an event and the edges between those nodes represents causal relationship. A given node can have can play any of these three roles. So a node could be a treatment, a node could be an outcome, or a node could be a mediator. So treatment is the first event that has occurred. Outcome is the last event that would occur, and then mediator are some intermediary events that would occur from the treatment to outcome. Let's take an example. Let's look at this particular relation, this network. So C causes A causes B, and then D causes D. So in just this three, if we just explicitly look at this relation, C is the first initial node. So that is the treatment node. D is the final node. So D is the outcome node. And A and B are the intermediary nodes. So A and B are the mediator nodes. The second concept we'll look into is called causal effect weights, which is a numeric value representing the strength of a causal relationship between the two nodes. And this is typically estimated by do calculus introduced by Dr. Yuda Pearl. And higher the value, so the higher the effect weight implies higher responsibility of something causing some other event. There are three types of causal effect weights, but we are only going to focus on the total causal effect, which is the effect of an outcome when you change the value of a treatment. So the treatment here is C. If you are to measure the total causal effect, you would change or set the value of the parameter C here and observe how does that affect the value of D. The third concept we'll look into is causal Markov assumption, which basically says in a given causal network, if we are given the parent of any particular node, let's say B, it is independent of its children. The fourth concept that we'll look into this presentation is called backdoor path, which is a non-causal path. So if we are trying to analyze the causal strength or a causal relationship between a given node pair, so let's take an example of the node pair A to B, and I'm trying to try to figure out what is the influence of this node A on the effect on this node B. So backdoor path is this non-causal path which affects, which is a common cause. So there's a common cause of both the nodes A and B, in this case the C, and in a way it introduces spurious association between this estimation of causality or causal relation in this given particular node and leads to inflated results. To avoid that, we have this backdoor criteria, which is a set of variable Z, which known to satisfy the backdoor criteria relative to an ordered pair. So an ordered pair here is Xi, Xj. For us, the Xi is A, Xj is B, which satisfies two conditions: that no node in Z is a descendant of Xi. So there should not be any node in this backdoor criteria set, which is a descendant of the node A. So B and D cannot serve as a backdoor path criteria, Then the second condition is Z blocks every path between Xi and Xj that contains an arrow into Xi. So there has to be an incoming edge into A, and it blocks every path going from Xi and Xj. So the only path that we see in this case is this particular path. So C satisfies our backdoor criteria in this case. There are two types of backdoor paths. There could be sufficient backdoor paths, which is a set of variables that blocks all the backdoor paths, and the maximum backdoor path, that's the largest set or the largest paths that would block all the backdoor without adjusting for descendants of treatments or outcomes. Now let's delve into the topic of the hour, causal neurosymbolic AI. So causal neurosymbolic AI, it's a fusion of causal AI and neurosymbolic AI. It combines the strengths of causality, neural network, and symbolic representation and reasoning. It aims to create systems that are powerful, efficient, explainable, and capable of reasoning about cause and effect. So the arrow from causality to neurosymbolic AI, which is the topmost arrow, takes the representation from the causal AI domain, that is the causal network, maps it into the symbolic space, that is the knowledge graph, and uses neurosymbolic AI techniques to solve a causal task. The bottom arrow takes the representation of causality from the symbolic space, maps it into the knowledge causal AI space, and use causal AI techniques to solve a causal AI task. My work focuses on the top half of the arrow. Now, why do we need it? We already have causal AI. What are the advantages of using this causal NESI, which I'm going to use interchangeably with causal neurosymbolic AI? The first advantage is user explainability. So causal AIs are dependent on the semantics of the model. So if I say stop line marking might mean something different for me, it might mean something different to you. On the other hand, on the causal NESI space, causal NESI provides additional semantics with the use of knowledge graph because it contains additional information about what are the characteristics of stop line marking. Scalability. Causal AI at the current stage, they are good with dealing with small graph. So they could scale well for the graph up to 20 nodes. But if you increase the number of nodes, most of the algorithms do not scale well. On the other hand, knowledge graph or the causal NESI part of it can easily include large graphs. Data. In the causal AI space, we are dependent on the observation data or the simulation benchmark data which are available out there. In the case of causal NESI, it can easily include prior domain knowledge in the analysis. Data integration and interoperability. Causal AI or the causal Bayesian network, they are not built for interoperability and the data integration. However, causal NESI can easily include the knowledge graph are well known for data integration and interoperability problems. Grounding. So grounding in causal AI is very low with the humans in the loop. However, in causal NESI, we include domain knowledge, so the grounding is strong or higher there. Reliability. So causal AI, I can develop a Bayesian network and say, no, there needs to be a link between the car stop causing the pedestrian to cross, not the other way around. However, in the causality part, since it's grounded or we have the domain knowledge, the data or the relations seems to be more reliable. Safety is model dependent. However, in the causality, we can provide additional safety constraints in the form of rules. Abstraction. So abstraction of the causal AI space is at the variable level. So I can give, maybe instead of saying stop line marking, I can even say ABC. However, in the causality, we have human level abstractions. Attribution, it's not possible to provide provenance information in the causal AI space. However, the provenance information can be easily provided in the causal NSE space. So using this framework, I made 5 contributions. First is in terms of representation. So the representation of causality from causal Bayesian network into a knowledge graph. So given any particular domain, we start with a causal network and we create a causal knowledge graph based on that. We transform the causal knowledge graph into the latent space and create 2 different types of transform the problem of causal discovery into causal link prediction. And in particular, we consider 2 link prediction tasks, causal explanation and causal prediction. So given the effect, explain what caused it, that is causal explanation, and given the cause, predict what would be the effect of it, that is causal prediction. For the evaluation task, we did 4 different evaluations. So we studied the influence of weights in the causal link prediction task. We took into account the causal Markov assumption while evaluating this causal link prediction task. So the causal Markov assumption was, given a particular node's parent, it is independent of its children. So we developed a Markov-based data split process, which would take that into account, and we saw significant improvement in the performance. The ones in the greens, which are the influence of backdoor paths in the causal link prediction and the influence of mediators in the link prediction, is what I'm going to talk about today. The earlier topics were already covered in the proposal beforehand. And then we saw the application of this framework in the autonomous driving. So I developed a driving scene causal knowledge graph for the link prediction task, and in smart manufacturing to study root cause analysis. In terms of representation, we had created two different type of causal ontology. One for the triple-based knowledge graph. So if the causal relationship is just as A causes B, it is represented as RDF. However, if you have a serial connection, which also has the mediator into this loop, which we transform into an hyperrelational knowledge graph, and we have 2 different ontologies to capture both of these nuances. So we have an ontology which would be just RDF based, and the other ontology which captures the hyperrelational base, which is RDF star and Sparkle star based. In terms of expressions and inference, we created 2 different types of embeddings: weighted embeddings, non-weighted embeddings, and weighted embeddings. So the non-weighted embeddings do not consider the weights into the evaluation framework, and the weighted embeddings captures the causal weights, which we studied, that was the total causal effects, into the evaluation of causal link prediction task. We evaluated our framework on 3 different types of graph structure, which varied in terms of domain knowledge. So the first graph that you see here only considers the causal relation. The second graph in the middle takes into account the causal relation as well as the type of the event. And the third graph takes into account the causal relations, the type of the events, and if there are any participants in the events in the frame. We use 2 different evaluation metrics. So MRRs, and these are one of the common evaluation metrics in the knowledge graph community: mean reciprocal rank, which is the average of the inverse of the obtained ranks of the links, and the hits at K, which is the ratio of prediction for which the rank is equal or less than a given threshold. Now let's look into the data set that we have used. So we use Cleverer Humans, which is a causal reasoning benchmark data set here. It consists of approximately 800 videos. And in these videos, there are multiple objects of different shape, size, material, color colliding with each other. And they have 27 different types of collision events. So the hit, push, slides or swipe swap, they all are all collision, but they semantically differ from each other. So if you look at this video here, we have an event that the brown cube collides with the purple cylinder, the brown cylinder rolls to the right, and so on. And all of this information is represented as a causal network, which basically is a serial connection of an event causes another event, and then that event causes a subsequent event. We did some pre-processing. So this network is formulated with the help of mechanical Turkers, where they were also asked to assign responsibility of the events causing the other events. So they were asked to assign the number 1 to 5. So higher the number, higher the responsibility of an event causing another event. So we can treat this as a causal relations and these numbers as a proxy to total causal effect that we just saw. We did some pre-processing. So the network they have is a fully connected network. We removed the nodes, the edges which were with weight 1, because that basically means that the weights, they are not causal at all. And we end up with a network that was suitable enough to say that fulfill the criteria of a Bayesian network. So if you just look at this network, there are no, this is at an instance level, and there are no causal roles associated with any given particular node. So we don't know which node is a treatment. Explicitly looking at it, we don't know which node is the mediator. And it does not contain any additional context information and the domain knowledge, which would be which network, which video this network belongs to, what are the different objects which are present in the networks. We just have these description, but we do not have the explicit information. What are the properties associated with the objects? So shape, color, material. And we also divided the events into two. We created this taxonomy where we divided the events into two categories: single object event, which just involved one object, such as enter, exit, and the binary object event, which involves two objects colliding, so hit, move, bump, and so on.
Utkarshani, sorry if I can interrupt. This is Michael Humes. Could you go
Yes, Dr.
back to that slide? You were just right there. Thank you. At the beginning of your talk, you mentioned a statement from Gary Marcus about the
Yes.
importance of time and space. So the additional knowledge that is captured here has time and space. So you list the events A, B, C, D through G. Those events happen in order. So that's time. You have additional information about time, and you can't have E happen before B. Next, there's information about space. The objects affect each other because they're roughly the same size and weight. And the objects, that ball, when it rolls, doesn't suddenly jump over one of the other objects and misses them because of spatial constraints and gravity. So that's very important additional knowledge that you have. And you don't, this is again, in addition to the causal knowledge, but you need to state that you have that additional knowledge. And that's very important for solving what happens and how causality works. Thanks.
Thanks, Dr. Hume. That's a valid point. And just to follow up on your comment, they had another variation of this benchmark that they have. So they had a couple of variations. They have first when just the photos, and instead of having videos, there were still objects. So this is the video version of the benchmark data set. Then they have another version of the same data set, which contained the physics information. So it contained the mass, the metal. So if it's like different shape and size, and I believe it also contained weights, if I'm not wrong. But in that data set, they had those association or those representation very explicit. In this data set, it's more implicit. But thank you for that comment.
So would there be situations where I may want to put the weight of the objects involved and or which heavy metal versus iron this and that, and if so, what would be the situation of the alternative other than yours and then your alternative in terms of capturing that information to improve the explainability. Your causal effect is a form of explanation. So, how would you capture that additional metadata and then use it to explain the behavior that you see here?
So the additional metadata can easily be captured if present into the knowledge graph. And in terms of the causal effects, so this study used mechanical Turkers for that, but maybe there could be some function that we can develop or define where we would give a higher weightage to a metal object versus a lower weightage. So let's say if it's a rubber object colliding, and estimate those total causal effect. So that is still an open problem in this domain.
So suppose you have a very heavy object and the ball is rubber ball, so then it might just
it might even just stop.
Yeah. So in that case,
or the other way around.
Additional knowledge of the data, explain,
why did it stop? Yeah. Yeah.
And where would you? I mean, maybe you can point out later on where such data to be used, because when you build the network from the data, the scope of incorporating the additional knowledge as variables, I don't see how that happens very well. But if you are going back to the knowledge graph and then using that to explain, I can see possibly happen.
So that would typically come under, so we had three different structure that we evaluated with. So we had type, we had participant information. We can have additional information like that. What is the material of that ball in the evaluation framework, in the knowledge graph part. Okay. So now let's look into the fourth concept that we talked about, which was the backdoor path. And let's take this example of a causal network where we have these events that a brown cube moves, causes the purple cylinder strikes the red cube, then the brown cube collides with the purple cylinder, is both causing the brown cube moves here and the purple cylinder strikes the red ball. And what would be your backdoor criteria? Just reiterating the backdoor criteria again here. If you want to associate or look into what is the causal effect of the A, how much A affects H individually, we have to make sure that we are not taking these variables or this common variable into account. So we have three different causal backdoor paths that could exist from this network. So one backdoor path could be from this variable G here. So the causal path could transfer or traverse from A to G, G to H. The second backdoor path could be A to G, G to D, D to J, and to H, and so on. And then the third backdoor path could be the edge from the causal path could go from A to E, E to B, G, B to G, and then G to H. So these could be possibly three backdoor paths that could exist in this causal network. This is the overall architecture of the framework. So we start with the causal network, which could either be learned from the observation data or provided by the domain knowledge. We remove the backdoor paths which are present in this causal network. We use our causal ontology that we have developed and transform that information into a knowledge graph. We create two different types of embeddings, one with the backdoor paths and one without considering the backdoor path into account. And we perform the task of causal link prediction, in particular two queries, so causal explanation and causal prediction. And here are some of the interesting results. So we saw that the backdoor path introduces spurious association, leading to inflated performance. So if we don't account for it, we will see a higher performance based on that. So we saw that the backdoor path, having the backdoor path in the link prediction task, had a bias of 31% in the terms of the embedding models which did not have weights. However, in the terms of embedding models which have weights, the bias was only 17%. And we also saw that including weights in these embedding models improves the performance. So performance goes from 0.21 to 0.49. So weights do affects the causal link prediction task. And we also saw that integrating the background knowledge, which was the type, and having the participants in the knowledge graph into this graph improves the MRR performance of the prediction task by 7.5% and explanation task by 8.8%. So now looking into the relations or the effect of having mediators into account. So what would be a mediator? So let's look into this serial connection, causal connection that we have. So we know there's a cause entity, it causes some intermediary mediator entity, and it causes the effect entity. If we were to represent this into the knowledge graph, which is RDF based, we would have to separate these two causal relations into two different triples. So the first triple would be cause entity causes a mediator entity, does not say anything about the effect entity or the subsequent event that would occur. Then the mediator entity causes the effect entity, again missing out the information about the treatment or the first event that has occurred. We can transform this information or map this into a hyperrelational form, hyperrelational graph form, which is RDF star based using the causal ontology that we have developed for it. And in this case, we just need one triple, which captures this all this context information. So in that case, the subject of the triple, which is the cause entity causes the effect entity, becomes the composite triple in a way. And then we have this hyperrelation of has mediator, the mediator entity. And we can have as many number of hyperrelations in this scenarios as need be. So let's take an example of the causal, the clever humans data set again, and look into this relation of this small network of C causes A causes B, and then C causes B. We have additional properties, and the events are the brown cube collides with the purple cylinder, causes the purple cylinder roll to the right. And this is what an RDF-based knowledge graph would look like. We would have causal relations between them. Along with the information of the event, we have the type information. So the event C is a type of move event, and then we have additional relations of the event C causes a type of collide, also causes a type of a roll event, which are A and B, and so on. And if we look into the serial or break it down into a serial connection of C causes A causes B, we can now transform that into a, instead of breaking it into two separate triples, we can now easily transform it into a hyperrelational form, and this is what it would look like. So C causes B, B then again caused by A, so that we had an inverse causal relation here. And then we have a hyperrelations of has mediator A, and then additionally, we have what is the mediator type. So we have additional cause hyperrelation of has mediator type collide. Following our similar architecture, starting with the causal network, now we directly transform into a knowledge graph, and we create two different types of embedding space. One is the base embedding space without the weights and just the simple triple base. And the second is the hyperrelational graph-based embedding. And we evaluate this on our causal link prediction task, that is the explanation and prediction. But in the link hyperrelational fact, we also consider, or the hyperrelational evaluation, we now also consider this mediator information or the context information, which we were missing out earlier. And we saw that adding these mediators or using these hyperrelations tremendously increased our performance. So point MRR improved from 0.33, 0.74, 0.77, then 0.31 to 0.77 in the case of prediction. And we also saw that integrating the background knowledge, which was the type and the participants, into the causal graph with these hyperrelations improved the performance on an average by 5.47%. So the hypothesis that we had was, to be very concise, can neurosymbolic AI framework be adapted to support causal AI tasks? And we looked into the representation. So we transformed and embedded the knowledge from causal network into the knowledge graph. We used hyperrelational knowledge graph to provide better context, which was the context of mediator. We did inference, so we learned incomplete causal net. So the problem of incomplete causal network was then mapped to the knowledge graph completion. We used weights in our knowledge graph prediction problem. We also incorporated domain knowledge or additional knowledge, which was the type and the participant information. And then we also looked at what are the effect of having backdoor paths. Does backdoor path introduce bias still in the knowledge graph space? Can mediators be represented as a hyperrelations, and what would be the effect of it? We evaluated it based on causal Markov assumption, which was not discussed in the presentation today, but was discussed in detail in the proposals. And we also saw that including the weights in this prediction task improves the performance, including the prior knowledge of the domain improves the performance. And by eliminating the backdoor paths into account, we were able to reduce the bias that were introduced by them and improve the performance of our task. And providing the contextual information further improves the performance of the hyperrelations. Yes.
You have referred to weights a few times. How do you get that information?
So in the cleverer humans, we used, so the humans have mechanical Turkers has annotated those numbers, and we use them as a proxy for weights. However, in the other work which I was doing on the side, we calculated weights based on the data we had and the Bayesian network that we created. So there are packages out there which can help us do that. So in terms of future work of this particular framework, I have identified 4 roles of causality in neurosymbolic AI. So the first is at the representation level, which is the causality for NESI. So applying causal principles to enhance neurosymbolic AI models and integrating causal representation and techniques to augment NESI models or neurosymbolic models. The second is the downstream task, which is causality in NESI, assessing the causal knowledge which is captured by the neurosymbolic AI method. So how does these models can reason about causality and understand this relationship? So in a way, I have achieved those things with these. So representation, expression, and inference dealt with causality for NESI. The evaluation and application dealt with causality in NESI. And then the third one, which is the integration. So causality with NESI talks about leveraging neurosymbolic AI models in improving the causal inference and discovery task. And the assessment is causality of NESI. So investigating the causal structure of the inherent neurosymbolic AI models. So making models more interpretable, which is crucial for some of the safety critical criteria. Some of the scholarly contributions that I have made so far throughout my journey. So I started working on my the healthcare project, and from that project, I had publication at journals like JMIR, Sleep, IEEE Sensor. I'd published at conferences on such as IC2S2, which is International Conference on Computational and Social Science, RTSI. I had submitted my work, published my work at workshops at ICHI and NeurIPS, and was also part of a 2 book chapters, an article on at IEEE Intelligent Systems. My work on neurosymbolic AI was published at ISWC conference, workshops at ISWC on ontology design pattern, and we had 2 articles on IEEE intelligent systems and internet computing. And since this work was done in collaboration with my industry collaborator, Dr. Rory Henson here, we submitted 3 patents based on this work. My third domain that I looked into or I worked on was industrial metaverse with Siemens, and we published our work at ISWC and article at Internet Computing. And based on the work, since also working with industry partners, you get to file patents. So we filed a patent which is still pending until 2024, last I checked. I recently organized the first workshop on causal neurosymbolic AI at ESWC, which is the Extended Semantic Web Conference earlier this month. And we got a huge response and a very positive response from the audience. We had it was full room with both industry and academic or people in the room. We had two keynote speakers, one from the causal AI domain and one from the causal NESI domain, and it was a huge success. So there was a good start towards this causal neurosymbolic AI framework. Some of the other contributions I have made, I was grateful to be invited to give a talk at a workshop on representation and reasoning at Knowledge Graph conference, which is the premier conference for industry and academic collaboration. I had given two tutorials, one on multi-agents in industry AI application at AMAS this year with my some of my colleagues here at AI Institute, and a tutorial on causal AI at the web conference. And I was recently asked to interview for the podcast at Data Skeptic on my work on backdoor paths in the knowledge graph. And one of our work was also featured in the Causal Python newsletter. None of this work would have been possible without my amazing multidisciplinary collaborators throughout. And along with them, I'd also got experience and exposure to work on grants. So at Wright State, during my time at Wright State, we worked with Department of Psychology on MURI, with the School of Medicine and Department of Computer Science in furthering our project on K-Health. That was the asthma project to study the interaction of obesity and asthma. Then I had collaboration in the university here with the School of Nursing. We looked into one of the proposal to motivational interviews for the adolescents, and then the McNair Aerospace Center. I have an international collaborator at Fujitsu, who was one of the organizers for the workshop as well. Some of this work has also been part of my work that I had done in my dissertation, was also done in collaboration with other undergrads and grad students. So one of the student that I had mentored from School of Nursing, she along with a high schooler, they had a poster at the university-wide research exposure symposium, Discover USC, and she got the best poster award. So I'm very proud of her and the work that they did on studying the asthma chatbots which are out there. Yeah, then I have other undergrad collaborators, Sarah, Utkarsh, and they helped me tremendously throughout my journey here. Some of the other professional activities that I have been part of so far. So I have been privileged to be responsible for like organizing and moderating the workshops, being an area chair, session chair lead at Machine Learning for Health, and the web conferences. I have been privileged to be part of the program committee, some of the top conferences. So web conference, KC, which was our in-house symposium that we had, and workshops at ICLR. I had also been privileged to be the reviewers for journals like IEEE Census, Nature Digital Medicines, Transactions on Fuzzy, and some conferences and workshops. I would like to, all of this work has been supported and was made possible by the grants that support that I have got from both NIH and NSF. So part of my work on healthcare was supported by the NIH award, and then part of my work on causality was supported by the NSF awards. I would also like to thank my committee members. So I would like to start with Dr. Sheth. He has been an amazing advisor, has always supported us and encouraged us to follow our passion. He'd never said, you have to work on this topic. He had always given us the freedom to explore our research agenda. So thank you, Dr. Sheth, for that. And I would also like to thank Corey. So there was a time in my PhD where I was like, it's not going anywhere. I don't think this is going to work. And this was during the internship, and he was always motivating me and was always there to support me in my research, and always like, no, this would work, and sat down with me and laid the outline that you see, this is how things are, you have to do, and there is a path forward. So thank you, Corey, for always being that motivating person. for me. Dr. Valtorta, he's been an amazing committee member and a guidance. I'd always would just go to his room, knock, and would just barge in sometimes. And when we moved to USC from Wright State, he spent numerous hours with me to help me understand causality. So my first tutorial that I got was from Dr. Valtorta, and he was always my go-to causality person here. So I don't think I would have looked into causality so deep if it was not for Dr. Valtorta's guidance. And my amazing other committee members, Dr. Hunes and Dr. Shallon, they've always been available for me. It's just like an email away, and they would respond. And they had been a tremendous supporter in my all this application process as well, and always been quick in responding to my queries. So thank you, Dr. Hunes and Dr. Shallon, for being available. This would not have been possible without obviously the fun that we have to do. So work hard, play hard. Without my amazing colleagues here at AISC. So we had some fun moments. So this was the Halloween picture that we took one time that we went on. And obviously we have this little kiddo who's, won't believe she's about almost a year old, and her parents are okay, but she's the one who's the the core energy of the energy of this lab. So whenever she's around, everybody just gets energized and just happy and smiling because of her. Oh, and this journey would not have been possible without the love and the blessing of my amazing friends and family. So some of the people in here know that this date was extremely important to me. So today used to be my mom's birthday, and I wanted to honor her by scheduling my dissertation on that. And thank you for helping me do that. And there was a time when I was thinking about I'll be moving so far away, I'm going to lose connection with my friends. I won't be able to see my sister growing up. So at that time, she was like, no, go do your thing. And just, I shared that with her. And that one sentence, she said, no, go do your thing, was something that just gave me all the strength. And I just took the decision of, no, I'm going to do it. So that's very special to me. So thank you, Mom, for that. And obviously, my dad, I had amazing parents. And everybody says that they have the best parents, but I'm going to say I have the best parents, because they have always been there for me, never questioned me ever in whatever I want to do in life. They have been very supportive. I don't think I have not seen any other parent do that. No offense, but I have the best parents, the best dad, the best mom, and obviously the best sister who's always just running around and making my life so much brighter. And the guidance and the support, I've grown up with my grandma. So she's the one who made me and confidence. So she'd always given me confidence since my kindergarten. I've stayed with her until my high school. So the confidence that everybody sees is based on the support that she had always given me, the mentorship and the guidance she had given me throughout my my journey. And my friends, so the pain, who's one of my closest friend here in US. I don't think I've cribbed about PhD to him throughout my journey. And he's always been supportive, always pushed me like, no, you got this, you can do it in his own ways. So thank you, Dupain, for doing that. And my amazing friends in India who have joined online, Bhageshwari, Deepshi, Kriti, Akshat, Nishtha, Kritika, Purvi, Shivani, and other friends who have joined online. Although we have moved so far away, they made sure that the connection is still there. After all these years, I still feel that we are still the same friends we used to be like 10 years ago. And my goofy friends here, Chris and Joe, they made my life very happening and amazing. We're always there to spend time and outside the lab here at USC. And one of my great friend, mentor, Manju Auntie and Sandeep Uncle, who are there in person here in the audience, they're a family away from the family. So I found a family here in Colombia. They treat me like a daughter, and they've always been there for me. So I'm very blessed and grateful for all the love and support everybody has given me throughout my life so far. And thank you so much. I'm open to questions now.
Well, thank you for the presentation. Now we should open the floor. We open the floor for questions. Typically, we have general questions first, maybe given priority to the audience, because the committee will have a special time with the candidate later. But questions from anybody right now?
Yeah, you can.
Hi, very elegant work. Where do you see the boundary and limitations with the formal reasoning as in sound and like you're dealing with causality, because you're dealing with knowledge, which is one or multiple domains. But then we go into the neutral part of this, right? Which is probabilistically getting doing the reasoning and getting the answer. So like with respect to formal reasoning as an improving or sound and like where do you see the interface?
That's a good question. And in a way, that's what I tried to do it with my framework here. So use some of the concepts which are exist in the causal AI and still map it to the neurosymbolic AI space. So the assumptions that was there in the symbolic part of it, or let's call it causal part of it, we were still able to map it to the neurosymbolic AI space. So there might be other theorems which exist in causality where maybe I will be able to implement it in the neurosymbolic AI space, but it's still fuzzy, I would say, right now. And especially if we think about are we going to use these evaluation framework or these models, or with the rise of LLMs, where would we draw the line? Or if we want to do causality using LLMs, how do we say that what is the formal part of and what is the neural model? So I would say it's still fuzzy at the moment here.
Hey, sorry, go ahead.
There's a question for the audience. I'll get back to you.
So I'm not in academia, and I liked your explanation earlier about the soccer ball in the neighborhood and the car stopped. And the soccer ball being on an interstate, it would not have stopped.
Yes.
As a consumer, I sit and I ride. I had my scariest first ride, but a really good ride after that in the autonomous driving vehicles.
Waymo.
Yeah. And so essentially, when I sat in the Waymo, I also saw there were people who were trying to go past the Waymo because it was paying attention and watching, what might happen. How do your models in the future, what do you predict is going to happen with the person who deliberately wants to break the law or try to bump into it? How do these models work in that environment?
That's a good question, Sandeep Uncle. So the question, was it audible to the audience, to the people online? Okay, I can repeat, Valerie. So the question is, how do we see these models that we are developing? He's not from the academic background. He's into industry. He's in industry. How do we see these models? So taking autonomous driving an example, see it working in real life when somebody would purposefully want to come in front of the car. And how would we do the representation? So in that case, I feel we definitely, the way currently the autonomous driving systems learn is just going onto the roads and collecting bunch of data. So Waymo is also collecting data. How many times? Maybe this is the intersection, which is a problem where people tend to jump in front. So they just learn on the observation data based. But with the approach that I have been proposing, where we have the domain knowledge. So even if there was one-off instance, it happened, we have the domain knowledge that these associations or causal associations are there. And with the help of causality, we can do counterfactuals. So what if something would have come in front? So one of the other work that I had done using the network that I showed you, the counterfactual would be, so the car is the car is just driving straight. What if a pedestrian comes in or a jaywalks? There is no stop line marking. What if a pedestrian comes in front of me or that's a jaywalking? How likely the car would stop? And in that work, we saw that the car is likely to stop. And we had two scenarios where the person with the object in hand, so it could be a backpack or a crate or a buggy, versus the person without any objects in hand. So the car is more likely to stop when there's a person with an object. So when you have the representation of causality in the AI model, we are able to deal with the counterfactual scenarios. So what you mentioned was one of the counterfactual scenarios.
Thanks.
Is it a follow-up or this one?
My question was along the same scenario. First of all, great presentation. Congratulations. So if you find the ball that's rolling into the road and you know that there's a field or a children's park around, you would know to immediately stop to a screeching halt as a human, right? And you could, when training an autonomous vehicle, you could incorporate that back. However, the counterfactual that I'm thinking of is, what if it's an old ball just lying on the middle of the road? It did not come rolling in. You do not assume that a child would come running after it. You could probably, as a human, when you're driving, you would think that, oh, this is just an old ball, I can just drive over it around. In this kind of a scenario, would your solution involve a backdoor path and just analyzing that? How would you go about differentiating these two scenarios?
That's a good question, Megha. So in that scenario, you would first use the domain knowledge, like where exactly the car is. So as Sandeep uncle mentioned, that the car is at the intersection versus not the neighborhood. And the backdoor path comes into play when there are common factors associated with it. So if there's a common factor between the car stopping, between the car causing, or between the ball causing the car to stop. So let's say hypothetically, the common factor could be kids in the neighborhood. So that's when the backdoor path comes into account.
So you could teach the model to consider both of the scenarios.
Yes.
Backdoor knowledge and then take a decision.
Yes. Great question. Dipen, you had a question.
Hey, so this is Dr. Patel. Great talk with Anthony. I have a two-part question. So the model, you mentioned the limitations of your model, and you mentioned pitfalls of your model. So I would like to kind of touch base upon both factors here. So what question is, it seems like the data that you had is very specialized. So what if you get a real life data, right? And the second question, so how would your model react to a real life condition? Would it hallucinate, or would it give you a more representative of what's actually going on in the real world? And have you looked at that? And the second part is the scalability. So it seems that you only have either 3 or 4 nodes at most in your neurosymbolic causal graph. So what happens, or how would the model behave if I start throwing in, you didn't mention that the model is scalable. In what sense is it scalable? And what are some of the pitfalls of your model?
So to answer your question on scalability, so that question I think arises from the comparison slide that I had, that causal AI is not scalable. The structural learning algorithms are good with up until 20 nodes. As the number of nodes increases, the most of the algorithms do not perform. However, when we transform this problem of causal discovery into the knowledge graph link prediction, we use the knowledge graph based methods. The knowledge graph inherently is a typically like hundreds of nodes, thousands of nodes in it, and lakhs of or hundred thousands of triples. So the algorithms or the embedding models which are developed for the knowledge graph, they are scalable or they are well equipped to deal with the large graphs. So the scalability part is taken care of once we transform this problem into the knowledge graph space, because the algorithms and the embedding models which are there are equipped, well advanced equipped to deal with it. The second question that you asked is how adaptable is this framework to real world application? So we did look into the real world application. So we had smart manufacturing set up here. So the model or the framework is independent of the number of nodes that you have. So it doesn't have to be, for now, for the example, I gave the autonomous driving a 3-node network for easy understanding. But if you looked into the clever human data set that I was dealing with, it had about 6 to 8 nodes on an average in the data. So it could easily scale from 3 node to 6 to 8. And in the smart manufacturing, I ran a traditional structural learning algorithm. And in that case, their case, the typical variables they have, the number of nodes they have, it is about 27 to 30. So it's easily scalable and it's easily adaptable to the domain that we are dealing with.
Thank you.
Thanks.
Are there any more general questions that one question now, especially again from the audience?
So there is working so-called causality club,
Mm-hmm.
and causality and neural networks have been investigated. There is Bayesian network work, of course, that's the foundational figure. That's statistical, am I right? And then you have a knowledge graph, that's symbolic, right? And then there is our own brand of symbolic AI, where there is a range from, although we have not completed all the investigation, from shallow, semi-deep, and deep infusion. Yours, embedding, which is shallow kind of thing. In the work that Kaushik has done, we have done semi-infusion order. Point here is that there are broad variety of representation and corresponding computational frameworks. Bayesian related things, knowledge graph related things, symbolic AI things, graph traversal things. And in the continuum of shallow to deep symbolic, there are a broad variety of things. Have you started to see any kind of start to understand the architecture that suits different problems? Obviously, they would all take different examples due to clever for a particular reason. But speak your many other examples really different than that.
So if we look into if the goal is for explanation or a better human explanation, neurosymbolic or the deep infusion and the shallow infusion that we have, those are deep infusion techniques, that those are the techniques that we would deal with if the human level explanation or the user explanation is the goal of the task. If it is a task of just scaling it in terms of just scaling the current structure learning algorithm or still being statistical, then deep neural network or the representation. So there's another field called causal representation learning. So those would be the streamline that you would be taking.
They would scale larger observational data, but they would not be doing exactly the same as what you.
They typically evaluate their techniques on the benchmark data sets. And there are like a few number of benchmark available out there. But if you're dealing with observational data, most of the time, or some few times that I have seen, we do not end up with true causal relations in those sense. And we do need domain expert in the loop to help us debug it. So that happened in the case of smart manufacturing, where I took the data, ran a few algorithms, and the relations I got were not intuitive and not causal.
Well, if there are no more questions from the audience, maybe we should ask the audience to leave and just do the committee here.
Are the kids here? I mean, it depends. It's going to take us.
Just stop recording.
Thank you, everyone, for joining. I'm going to stop recording. So this is a closed session. So people online, except the committee members, can leave. Thank you for joining.
Thank you, Utkarshani.
Thank you.
Thank you, Utkarshani.